Hello and welcome. I'm Mario Plasencia with ActiveArc in Switzerland. Today, I'll review ultrasonic impact peening, what it is, and how it's used. If you weld or produce welded structures subjected to repetitive stress, this information may help you make a value decision on whether the technology will help improve your products or services. If you have any questions after this presentation, you'll find my email and website details so you can contact me directly. Let me start by telling you a bit about my business. ActiveArc has been in the business of high-power ultrasonics for the past 17 years. We provide expert application advice and develop innovative high-power ultrasonic solutions to a wide range of industries, including medical devices, food, oil and gas, tube and wire drawing, chemicals, wastewater treatment, plastics, metals, and also new applications with research and development centers and universities. In 2004, about 14 years ago, we were asked to develop an ultrasonic impact peening system for a service client that wanted to use these systems primarily for offshore weld repair and vessel life extension. We started delivery of those systems in 2005 and have since made a number of progressive design improvements. We are one of the most experienced ultrasonic impact peening suppliers on the market, and we offer very high quality and reliable products. So let's get started. Ultrasonic impact peening tools use an ultrasonic transducer to make strong and uniform vibration of one or more pins that in turn hammer a surface to be treated. The key to the technology's success and industrial acceptance is the ability to make high-frequency hammering at regular intervals. This means that it provides a better and more uniform result compared to other impact technologies. Plus, ultrasonic peening can be significantly more ergonomic to the operator. Other impact peening technologies, such as pneumatic peening tools, are known to have issues with excessive vibration that can lead to operator fatigue and may cause physical discomfort or even some harm. I'd like to point out that there's some confusion about the names used for ultrasonic impact peening. Research papers and industrial websites are using a variety of names interchangeably. Other names you may find used for ultrasonic impact peening include simply ultrasonic peening, ultrasonic impact treatment, ultrasonic hammer peening, and ultrasonic needle peening. I'm also going to include on this list high-frequency mechanical impact. Now, this last one is really confusing. It typically refers to pneumatic hammer peening that also use one or more impact pins. In this case, the important difference is related to the peening impact frequency, where ultrasonic systems offer a higher rate of impact for a more uniform result that is very important to the work finish. I've seen references to high-frequency ultrasonic impact peening, so you can see the names are similar and confusing. I also want to differentiate from shot peening. Now, this is a technology that uses shot, that is a round metallic glass or ceramic particle that's thrown with pressure randomly against a treated surface. Conversely, our ultrasonic technology uses a pin to hammer a surface at regular intervals. So why would you use ultrasonic peening? The main reason is to strengthen the fatigue life of welded elements, structures, and metal parts. This is done by relief of tensile residual stresses that can be down to a depth of up to 12 millimeters, and introduction of compressive residual stresses into treated surface layers down into the range of 3 millimeters. In weld toe zones, it will decrease stress concentration and effectively remove minor crack-like flaws. It will enhance the mechanical properties of treated material surface layers, and it can increase hardness of material surfaces. This is done by stimulated changes to the intergranular composition of the metal. This happens below the surface. Ultrasonic peening can modify the size, shape, and orientation of grains within the material. Fatigue testing of welds treated by ultrasonic peening shows it's the most efficient post-weld treatment compared to traditional techniques such as grinding, TIG dressing, heat treatment, pneumatic hammer peening, and application of low transformation temperature alloys. It improves corrosion resistance of welded elements and treated surfaces. It can eliminate distortions from welding and other heat or bending processes. Ultrasonic peening may be applied for fatigue life improvement during manufacturing or repair of welds. So where is ultrasonic peening applied? Our main application is treatment of welds. However, it can also be applied to formed and machined metal parts to relieve residual stresses. While all welds can benefit from ultrasonic peening treatment, it becomes most important on surfaces that are subject to repetitive stress, such as tower structures. Wind generator towers are a particularly good example. Shipbuilding, especially ships subjected to frequent on and off loading, pipelines, railway and motorway bridges, construction and heavy equipment, military heavy vehicles, crane frames, and I should also mention brackets and web frames of structures. Again, the idea is to reduce tensile stresses, introduce compressive stresses, and remove surface defects. Aside from weld treatment, ultrasonic peening can also be used on surfaces of critical parts where strength and wear are issues. In these cases, the treated parts show reduced rate of near-surface micro-pitting fatigue, and this is due to increased surface hardness, improved surface quality, and lower roughness average values. Now, let me briefly review how it's done in weld treatment. The principal area of focus should be the weld toe to gain significant weld fatigue life improvement. The peen groove width should be in this range of 2 to 7 millimeters. The optimum is somewhere in the middle at 3 to 6 millimeters. The groove depth should be in the range of 0.2 to 0.6 millimeters. This groove is made by surface plastic deformation of material during ultrasonic peening. Let's have a look at the system and its working parts. Let me show you one example of a hand tool. Bear in mind, this can be easily converted to a robotic tool by changing the handle to a mounting assembly. But for now, let's stick with this hand tool and review the required elements. First, the external elements include a clean and dry compressed air supply. Usually just 1 to 3 bar pressure is sufficient. This is used for cooling the hand tool internally and the impact pins at the working end. There's also an ultrasonic generator power supply. This takes mains power such as 115 or 230 volts AC and converts it to a special high-frequency, high-voltage signal to drive the ultrasonic transducer. Now let's have a look inside the hand tool assembly. Starting at the top, there's a spring shown here in brown represented by this coil that's used to press the ultrasonic assembly down towards the peening pin. The spring provides needed flexibility and controllable pressure to the pin and also significantly reduces vibration to the operator. Next is the ultrasonic transducer, shown as the light blue pieces together with the brown elements, and that would be this top piece plus these elements and this bottom piece here. In this case, it represents a piezoelectric transducer. This transducer converts electrical energy to physical vibration. Attached to the bottom of the transducer is a boosting sonotrode shown in darker blue here. This is used to boost, or you could say increase, the end vibration displacement by some factor of 2 to 4 times. The goal is to achieve vibration in the range of 30 to 70 micrometers, more or less, depending on the application. The red piece at the bottom of the blue sonotrode is an optional replaceable tip. The sonotrode tip is subject to wear, and this is an option for simplified field maintenance. Then there's the impact pin shown here in purple. It can typically have a diameter of 4 to 6 millimeters with a tip radius of 2 to 3 millimeters. These pins can be custom designed for other shapes and diameters as required. The pin retainer cap is shown in brighter green, and this is used to keep the pin in place. It's removable so that the pins can be maintained and replaced in the field. Now I'd like to show you a brief animation. It demonstrates the interaction of the internal parts of the hand tool. First, you'll see that when the tool is pressed down to the work area, the purple impact pin is pressed up to contact the red tip of the ultrasonic assembly. With only minor pressure here, there will start to be some small impact action between the pin and the treated surface. To achieve more significant impact energy, enough to make plastic deformation of the metal surface, it's necessary to push the pin further up to make additional loading contact. This will move the ultrasonic assembly up and engage the spring pressure, thereby creating more peening energy. Once in this state, the pin oscillates at a regular frequency between the sonotro tip and the surface being treated. Before we wrap up today, I'd like to briefly review what we do at Active Arc Ultrasonics Group. As I noted earlier, we develop ultrasonic impact peening systems, and we can customize them to a wide range of requirements. These systems can be adapted by variations in output energy, impact pin shape, and the number of pins. Different metals require more or less impact energy to achieve the desired result. Softer metals can be treated faster and with less energy than harder materials. Adjusting peening energy is a basic function of all of our systems. Energy output is a function of many factors. First, system operational frequency. Today we produce systems at 20 kilohertz and 35 kilohertz, and we can make other custom frequencies as required. Another factor is the amplitude of the ultrasonic vibration. Now, this is achieved through a combination of electronic control and mechanical design of the internal elements. A third factor will be the pin tip shape and the number of pins. We offer a number of standard configurations, and we can easily customize these or design new arrangements for our clients. A fourth factor that influences the peening hammer energy is the applied force. We have some proprietary techniques that allow us to customize this force, and we work with our clients to adapt to their specific needs. I hope this presentation has served you. Before I get to a couple of commonly asked questions, I want to invite those of you that think ultrasonic impact peening could be useful in your business to continue the conversation in private. I offer a 45-minute strategy session with me directly. It's totally free. We can discuss your application and determine solutions that can best fit your business. We'll get clear on the challenges that you may face and make a plan on how we can help you. Today, I've given you just a brief overview of what ultrasonic impact peening is, where it can be used, how it's used, and why you should use it. Each business is unique and has its own requirements, so it's helpful to discuss individual challenges. That's why I offer a private strategy session. So send me a message and let's set up a time to talk. I have a couple of common questions that I'd like to share. The first one is, what is the weld treatment speed? The answer is, this will depend on the type of metal and whether you're treating a new weld or repairing a weld. Generally, the peening rate will be somewhere between 200 and 400 millimeters. So on average, we could say about 300 millimeters per minute, and that's about 12 inches per minute. A second question is, what are the maintenance issues for ultrasonic peening equipment? I would answer this way. All elements inside of the hand tool can over time require some maintenance and eventual replacement. The most common maintenance issue will be the peening pins and the tip of the ultrasonic assembly that's in contact with those pins. The pins should be considered wear parts, and spares should be made available to the operator for field replacement. The ultrasonic tip, depending on the design, may be a field repair, or it may need to come back to a technician for factory repair. Okay, that concludes my session. Thank you for taking time to listen. When you have follow-up questions, please don't hesitate to contact me. Thanks again, and bye for now.